Alright everyone, so in this video we are going to wrap up everything to do with derivatives and applications of derivatives, and then the next couple of videos that we're going to do are going to be on undoing a lot of the stuff we've done with derivatives, or at least an introduction to that and more what you'll see when you get off to Calc 2. Okay, so there are two topics that we want to talk about, and one of them is going to deal with approximations. So the main idea is that we have some function f, and it's going to be differentiable around a point A, and what we'd like to do is approximate that function by some other function, capital F. So the idea is maybe we have a very complicated function, and we're really only interested in what's going on around a particular point, so we don't need necessarily all of the complexity of the function, and we'd just like to approximate it with something simple. So the usual one is a line or maybe a parabola. Okay, so the question we have is, what properties would we like this approximation to have? Well, one thing that we would like is at least capital F and little f to be the same value at A, because that's kind of what we're going to be concerned with. We're concerned with what's going on around A, and maybe something else that we would like them to have in common is we would like our function and the approximating function to have the same derivative at A. Well, this is conveniently just the tangent line equation, right? So we said that the tangent line has both of those properties. It evaluates to the same thing as the function at the point in question, and the tangent line has the same slope as the function at the point A, and and so that's going to give us what's called the linear approximation to x, or to f of x at a point A. So we'll call it L of x, L for line or linear. So L of x is going to be equal to f prime of a times x minus a plus f of a. Okay, so we'll do a couple of examples of this. So the first one that we'll have is we'll want to linearly approximate the square root of x plus 1 at x equals 0, and we're going to use that to approximate the value of the square root of 1.1. Okay, so I'll come back to the picture in just a moment. So what we're going to do is we're going to have a equals 0, and we're going to find our derivative is just 1 over 2 times the square root of x plus 1. And then we're going to put everything into our tangent line equation. So we'll get f prime evaluated at a will give us 1/2. Then we'll have x minus 0 plus the square root of 0 plus 1. So our linear approximation will be x over 2 plus 1. And then we said that we want to approximate the value of the square root of 1.1. So one mistake that you might make is to put 1.1 in here for x. What you want to do is you want to ask, what is the x value that I need to put in here so that f of x is the thing you want to approximate. So here we want to put in x equals 0.1. That way f of 0.1 will give us the square root of 1.1, which is the thing we want to approximate. So when we put in 0.1 for x, we get 1/10 over 2 plus 1, which is 1.05. So we're saying that the square root of 1.1 is approximately 1.05. And if we wanted to find what the square root of 1.1 is, you would find it's 1.0488, and then more values afterwards. So one of the ideas you could think about what we're doing with linear approximations is, in effect, you are asked to get a reasonable approximation to something, like in this case, square root of 1.1, but you don't have a calculator to get the exact answer. You need to come up with some way of approximating it. Okay, so pictorially, kind of the idea that we're doing is this. We've got some main function that's here with the black curve, and around some point A, we want to approximate the value of the function. And we're going to do it with this magenta line. So the idea is this. So we go over some value x, Well, we'd get the exact value of the function, so f of x, but then we'd also have the approximating value from the line, which we could find by f prime at a times the delta x, so how far we've gone over on the x-axis. And the idea is that so long as the function is reasonably well behaved and you're not too far away from where you started, the difference between this approximating value and the actual value is going to be fairly small. So that's kind of the pictorial idea of what we're doing. Okay, so the next one. So we want to approximate the function 1 over t around t equals 5 to get an approximation for 1/7. So here we're going to take a to be 5, and we'd find our derivative from the power rule to be minus 1 over t squared. So we get that our linear approximation is our g prime of a times t minus a plus g of a. So minus a 25th times t minus 5 plus a fifth, and we'd find that we wind up with minus t over 25 plus 2/5. And then what we said is that we want to approximate 1/7, so we'll go and put in t equals 7, because that's the t value we would need to put here to get 1 over 7. And when we do that, we find that our linear approximation value is going to come out to be 0.12, and if you want to find 1/7, you get that's about 0.143. So again, reasonably close. The other thing you can do if you're checking your work for homeworks or something is if you do a linear approximation and you get a value that is wildly different from the actual value, so here if you put in 1/7 and you get something wild, or you put in a value for your linear approximation and you get an output that's wildly different from the actual value of 1 over 7, it says maybe you've done something wrong, you want to go back and just make sure you've got everything done right. Okay, so let's come up with a linear approximation for sine of x around x equals 0. Well, we're doing this around 0, so we're going to take our a value to be 0. The derivative of sine is cosine, so our linear approximation is going to be h prime of 0 times x minus 0 plus h of 0, and when you evaluate that, you just get x. So in other words, what this is saying is that around x equals 0, sine of x is approximately x. And maybe those in physics or engineering or something, if you haven't come across this, you will. And maybe this isn't too surprising. So in the video on plotting functions, I mentioned that sine, if you write it out as a polynomial expansion, you would get x minus x cubed over 3 factorial plus x to the 5 over 5 factorial, and so on. And if you just take the linear part of this, there's no constant term, and the only pieces that show up with degree of 1 or smaller is just this x. So maybe this result isn't that surprising. Okay, so then we can talk about what are called differentials. So the idea with a differential is that you have a function f of x, and what you want to see is maybe at a particular point, if you vary the input slightly, how much are you going to change the output? And what we're doing with this is we're getting the approximating line. So we're taking the idea from kind of this picture, this f prime of a delta x, to be our differential. So the exact, so you could find the exact difference if you wanted, and I'll come back to that in just a moment, but what we're going to do is just approximate things. Okay, so we'll ask, what is the worst possible case error that we could get for the area of a square that has side lengths of 5 centimeters with a measurement error of possibly 1/10 of a centimeter. So the idea here is you're measuring something, you have measurement plus a measurement error, and you want to see something like how much you could be off. Okay, so the idea is something like this. So we have a square, it has side lengths of u, and then we have this measurement error delta u kicking around. Well, the area that we have for a square is our side length squared, and what we want to find is the derivative and then multiply by our error estimate to get our worst case scenario. Okay, so the delta A is going to be approximately 2s times ds, so ds is going to be our measurement error. And when we plug in the 5 centimeters for s and the tenth of a centimeter for ds, we get that the worst case area is off by roughly 1 square centimeter. Okay, so let's see what all of this is representing from the picture. So we have the square inside the black box, and that would be our area. The worst case scenario that we could get for the area is when the measurement error is off by the most possible, so in this case 0.1 centimeters in both directions. And what you're going to get is you're going to get a bigger square where you're going to have some extra area kicking around. So we're going to have this one segment on top that's going to have a length of, in this case, delta u and a width of u. So from what we've said, u is 5 centimeters, delta u is a tenth of a centimeter. So you'd get a half centimeter squared up here. And then over on the right-hand side, you're going to have a length of a tenth of a centimeter and a width of 5 centimeters. So you're going to get another half centimeter squared from there. And then you're going to get this little square sitting up in the top right. And it would have lengths of 0.1 centimeters on both sides. So you'd get 1/100th of a square centimeter from there. So the exact change in the area that you could wind up with is just the sum of the areas from these three pieces, and that would go and sum up to 1.01 square centimeters. And what we did was just approximate the worst case change in the area, and we found it's 1 centimeter squared. So by finding the derivative, we can simplify out a lot of the work that we would need to do. Okay, so we can do the same kind of idea, but now we're going to do it with changing the radius in the volume of a sphere. So we're going to have a spherical snowball, and we want to see how much the volume is going to change as the radius drops from 5 centimeters to 4.92 centimeters. So the volume of a sphere is given by 4/3 pi r cubed, and if we find the derivative of the volume, we would get 4 pi r squared. So from what we said back here, our differential is going to be, in this case, dv is going to be given by f prime, or in this case v prime of r times dr, and that's approximately going to be the total change in the volume. Okay, so when we go and we put in 5 centimeters for r and minus 0.08 centimeters for dr, because the radius is going from 5 centimeters to 4.92 centimeters, when we multiply everything out, we get that our change in the volume is going to be approximately 25.13 cubic centimeters. Again, as before with the square, we could go and find the exact change in the volume here. So the exact change in the volume is going to be the final volume minus the initial volume. And if we did that, we'd have to take this r plus dr and expand everything out. So when we do it, we get this kind of expanded bit. And we see that the initial volume that we had is going to cancel off with one of the terms from our expansion. So we get these three pieces remaining. We get the 4 pi r squared dr, which is what we've said here, and then we get two more terms. And what we see is that the exact volume that we would get is about minus 24.73 cubic centimeters. So again, fairly close to what we've said for the approximate volume. Okay, and one of the ideas is that we're really dropping off these last two terms. We're dropping off these two terms. And the reason why this kind of works is that in comparison to the actual radius size that we're working with, the dr is fairly small. We're looking at a radius of 5 centimeters, and the drop in the radius is 0.8 centimeters. So in comparison, quite small. Well, when we're looking at something where the difference between the radius and the change in radius is small, when we square that change in radius, we're getting something very small. And when we cube that change in the radius, we're getting something very extra small. And in effect, what we're saying is, if we discard the very small and the very extra small parts, we're not going to change things that much. We've done most of the work, and we've got the bulk of where the change in the volume is coming from. It's coming from just this one term. The other stuff isn't going to contribute that much, and it's just not worth the effort to find it. Okay, so then the last thing that we want to say here is we want to talk about 4 different kinds of errors that you could have. So the first kind of error that you could have is just the absolute error. So just the difference in the exact value minus the approximating value. Right, so depending on the problem that you could be working on, you might get an absolute error of 1/1,000,000th of a centimeter, or maybe 1,000,000 kilometers. Okay, so that's good, but then you might want to know, well, how good is your approximation? You would say that maybe if your absolute error is 1,000,000 kilometers, maybe that's not too good. But if you're working on the scale of galaxy sizes, maybe 1,000,000 kilometers isn't that bad. And you might also say that being off by 1,000,000th of a centimeter is quite good. But if you're working on the scale of 100,000ths of centimeters, maybe being off by 1,000,000th of a centimeter is not actually that good. So that leads us to kind of the idea of relative error. So the relative error is we take the absolute error and we just divide it into the exact answer. So for us, this would look like delta f divided by f, so the change in the outputs divided by the original. And as we had before, we can approximate this with the differential df divided by the actual value f. We could take the percent error, which is just going to be the relative error multiplied by 100%, because sometimes we'd rather talk about percents. And then there's the propagated error. So the propagated error is kind of what we were just looking at. So the exact change in the y values is the exact difference in the outputs by changing the input a little bit. And as we just said, that's approximately the differential. So the f prime of x times the change in the input. Okay, so we're going to take the radius of a ball bearing to be measured at 7/10 of a centimeter, and we'll say that the measurement is correct to within 1/10 of a centimeter. With this, we'd like to estimate the propagated error for the ball bearing and find the relative error. So one thing that we could see is our measurement is only 7/10 of a centimeter, but the measurement error is 1/10 of a centimeter, so we would expect this to be quite bad. Because proportionally, the measurement error is quite big in compared to the size of the actual measurement. Okay, so as before, we have a sphere, so our volume is going to be 4/3 pi r cubed, and our derivative is then 4 pi r squared. So our propagated error, so our change in the volume, is going to be approximately the derivative of the volume times the change in the radius of the measurement error. And here we'll get is 4 pi times 0.7 squared times 0.1. And when you multiply all that out, you get about 0.616 cubic centimeters. Okay, and then for our relative error, we're going to take our dv divided by v, so our v prime of r times dr, all divided by the volume. And when we cancel off all of the similar terms, what we wind up with in the end is 3 times the measurement error, all divided by the radius. And that's going to be 0.42. So in other words, the percent error that we're going to get here is 42%. So as I said, something pretty bad. Okay, so that goes and gives us what we need to know about various error measurements. So the second topic that I want to do here to wrap up everything that we need about derivatives is what's called the mean value theorem. Okay, so one theorem that we're going to use just as a precursor to the mean value theorem is what's called Rolle's theorem. So the idea is that if you have a continuous function, you're looking at a closed interval a to b, and your function's also differentiable inside the interval a to b. And we also have the condition that the two endpoints of our interval evaluate to the same place. Then there's going to be some place, some value c in between a and b, so that the derivative is 0 at that point. Okay, so what we want to do is find an interval for the function x cubed minus 7x squared plus 10x so that Rolle's theorem applies. Okay, so in other words, what we're trying to do is find two places, find an a and a b so that f of a and f of b are the same thing. So the easiest way to do this is find two places so that f evaluates to 0. Right, so what we could do is we could factor f to get that f is going to be equal to x times x minus 5 times x minus 2. And from this, we could see pretty simply that any of these three intervals, 0 to 2, 0 to 5, or 2 to 5 will work because f of 0, f of 2, and f of 5 are all 0. Okay, and our function looks kind of like this, and what we'd see is that in between 0 and 2, there's this point here, looks like just to the left of 1, so that the derivative is 0. And then in between 2 and 5, there's this point that looks like it's maybe a little bit to the left of 4, so that the tangent line would be flat there, so the derivative would also be 0. Okay, so then the mean value theorem is taking Rolle's theorem but extending it slightly. So what it says is that if you have a continuous function over closed interval a to b, and your function is differentiable in between a and b, then there's going to be some c value in the middle so that f prime of c is equal to f of b minus f of a all over b minus a. Another way of saying this is that there's a point c in between a and b, so the instantaneous rate of change at c is equal to the average rate of change over the interval a to b. So remember that this expression on the right is the average rate of change over an interval a to b. Okay, so two examples for this. So we're going to find the c value so that the mean value theorem applies for f of x equals the square root of x over the interval 0 to 1, and then we're going to find the c value guaranteed to exist by the mean value theorem over the interval minus 2 to 2 for x cubed minus 3x plus 1. Okay, so I guess really the first thing that we should do is we should make sure that the mean value theorem applies. So we're looking over the interval 0 to 1. We first want to make sure our function is continuous. Well, the square root function is indeed continuous over the interval 0 to 1, and it's also differentiable on the open interval 0 to 1. So we don't have to worry about the two endpoints, and the square root function is differentiable on all the positives. The inside of the interval 0 to 1 is only positive numbers, so the mean value theorem will apply, and now we're just going to go and find the c value guaranteed to exist. So we get that our derivative is 1 over 2 square root of x, so we're going to solve f prime of c equal to f of b minus f of a all over b minus a. So on the left hand side we get 1 over 2 square root of c, and on the right hand side we'll evaluate at 1 and 0, and we get square root of 1 minus square root of 0 all over 1 minus 0. So we get 1 over 2 square root of c equals 1, and solving for c we get 1/4. Right, so here we have a plot for the square root of x in blue. The red line is the just the secant line connecting the two endpoints, and what we see here is at a quarter, the tangent line there is parallel to the secant line. So in other words, we found a point where the instantaneous rate of change and the average rate of change are the same thing. So the instantaneous rate of change at a quarter is the average rate of change over the interval 0 to 1. Okay, so then we'll do the same kind of thing for the second example. This one's much simpler because it's a polynomial, so it's differentiable and continuous everywhere, so the mean value theorem applies. So now we'll go and find the c values that exist as guaranteed by the mean value theorem. So we find that our derivative is 3x squared minus 3, and the slope of the secant line, after simplifying everything down, we'd get to be is just 1, right? Slope of the secant line is just 1. Okay, so when we add the 3 to both sides, we get 3c squared equals 4, and solving for c, we get plus or minus 2 over the square root of 3. So in this case, we get 2 points where the tangent line at these points is going to have the same slope as the slope of the secant line. So the mean value theorem guarantees the existence of one point, but as we have here, you could have multiple points that meet this criteria. Right, so here from the plot, again, we have the function x cubed minus 3x plus 1 is given by the blue curve. The red line here connects the two endpoints, and these two tangent lines are parallel to that secant line, and that gives us the two places where the slope of the secant line it has the same value as the slopes of the tangent lines here at plus or minus 2 over square root of 3. Okay, so the absolute value function gives us an example of why we need to actually make sure that the conditions apply in the first place. So we need to make sure that our function is continuous over the entire interval and differentiable over the inside of the interval. If you just blindly went ahead and said, well, find the c-value guaranteed to exist by the mean value theorem for absolute value of x over the interval minus 1 to 1, you would wind up with something weird like this, because there is no place over the interval minus 1 to 1 where the slope of the secant line and the slope of the tangent line matches, because the slope of the secant line is 0, and for all the points here, the slope of the tangent line is either 1 or minus 1. So you're not going to get a point that has the slope of the tangent line equal to 0. And the reason for this is because the absolute value function isn't differentiable over the entire interval, and that's what you need to exist. Okay, so then just a couple of results to wrap up here. So if you have a function that is differentiable, and you're told that over some interval the derivative is always 0, then the function is a constant. The reason for this is that you take any 2 points in your interval, well, f of b is f of a. So you have f prime of c equals 0. So, what we wind up with is flat tangent lines, but we get flat tangent lines everywhere on the interval because we can choose a and b as however we like. So everywhere inside of your interval has a flat tangent line. That says you have to have a constant. You have to be dealing with a constant function. And then a related result to that is if you have two functions that have the same derivative everywhere over an interval, then then they just differ by a constant. So the reason for that is take a new function h and call it the difference between f and g and take that derivative. Well, because we said that f prime and g prime are the same thing, the derivative of h is just 0. So if h prime is 0 everywhere, that means that h has to be a constant from what we just said. So it tells us that f minus g is a constant, so just the two functions differ by a fixed constant. Okay, so that's everything that I want to say about the mean value theorem. So I'll have a worksheet sitting in while courses over these topics, and in the next video we'll start talking about how we're going to undo derivatives. And I'll see you then. Bye.